Section 1 in Chapter 3 talks about solving systems graphically. So before we can talk about how to solve them graphically, we need to know what a system is. When you have two or more linear equations, it forms a system of linear equations. So you take one equation and another equation, or more than just two, you put them in the same problem, they become a system. When you solve that system, two equations gives you two answers, typically an x and a y. That ordered pair makes all of the equations true and is considered to be a solution of the system. So you're going to notice that most of these solutions are ordered pairs. Later on in the chapter, you'll have three equations, which makes it an ordered triple. So there are two basic ideas behind the number of solutions. So we have solutions. That's considered to be consistent. And then we have no solution. That's considered to be inconsistent. So inconsistent systems stand on their own, meaning that if there's no solution, it's considered inconsistent. But if there is at least one solution, it's considered consistent. Just one is independent. And many is dependent. So you're going to find when they talk about these questions, you will either call them independent, dependent, or inconsistent. So graphically, here's what it looks like graphically. Here on the left, we have one solution because those lines intersect one time. It's called an independent system, and it is consistent because it has a solution. The line in the middle is kind of tricky. It almost looks like there's only one line. It's because both lines happen to fall on top of each other, and it ends up being the same line. It is still consistent because it has at least one solution, but we call it dependent because it has infinitely many solutions. You're going to find me abbreviating infinitely many solutions with IMS, so you know what that stands for. And then the last one all the way on the right is no solution. No solution means it never ever intersects, which is considered parallel. We call that an inconsistent system. So the first set of examples. What is the solution to the system solved by graphing and check? So you're going to have to graph each line separately and see what's going on. So I'll do this one in green so you can see the difference. X plus y equals 4 is not ready to be graphed. You have to solve it for y to be able to graph it. Subtracting x from both sides gives me y equals negative x plus 4. And take a second and graph that. Now I will say using a straight edge is really important in these questions because if your lines don't lie on the xy axis as well as they should, then it's not going to be as reliable as you're used to. Y equals negative x plus 4 is a line that crosses at positive 4 and goes down one to the right one a whole bunch of times until you can confidently draw in a line. I'll do the other equation in red. 2x minus y equals 2 is also not ready to be graphed. I'm going to start by subtracting 2x from both sides. Subtracting 2x leaves me with a negative y equals negative 2x plus 2. And dividing everybody by negative 1 gives me y equals positive 2x minus 2. And take a second and graph that one as well. It is a line that crosses at negative 2 and goes up 2 and to the right 1, up 2 and to the right 1 a bunch of times. Take a second using a straight edge and get your line on there. There are two sets of directions they're going to give you. The first is going to be solving, and that's what they're asking us to do here. And the second is determining what kind of system it is. Technically speaking, this is a consistent, independent system. Consistent because it has an answer, it intersects. Independent because it only intersects once. And that happens right here. Because the directions say what is the solution or solve, I'm looking for an ordered pair. That ordered pair is 2, 2. X is 2 and y is 2. So my answer is 2, 2. It does say you can check. That just means putting that x value of 2 and y value of 2 into both the equations, and you should find that they are true. What is the solution to the system solved by graphing? Tell whether the system has one solution, infinitely many solutions, or no solution. I'll repeat the same process. I'll do this top one in green. 2x plus 3y equals 12. I'm going to solve that for y. Start by subtracting 2x from both sides. I get 3y equals negative 2x plus 12. Divide everything by 3. Gives me y equals negative 2/3 x plus 4. That is a graph that crosses at positive 4 and goes down 2 to the right 3 a couple of times. And then draw in a line. I'll do the second equation in red. X minus y equals negative 4. I'm going to start by subtracting x from both sides. Gives me negative y equals negative x minus 4. And dividing everything by negative 1 gives me y equals positive x plus 4. That's a graph that crosses at positive 4 and goes up 1 and to the right 1. Take a second and use a straight edge to get that line on. You should see that these lines intersect right there on the y-axis, and that ordered pair is 0, 4. That's the solving part. It then says, tell whether the system has one solution, infinitely many, or no solutions. This system has one solution. The number of solutions matches the number of times it intersects, and that graph intersects 1 time. It's considered to be a consistent, independent system. Letter C, the top equation is already solved for y, so I'm just going to take a second and graph that. Starts at positive 9, goes up 1 and to the right 2. If I do that again, I run out of room, so I'm going to go down 1 and to the left 2, because if not, my graph isn't as accurate as I need it to be. Accuracy is key in these questions, because if not, they might not line up exactly where they need to, and then you won't see the answer. The second line is not ready for me to graph, so I'm going to start by adding x to both sides. It gives me 2y equals x plus 1. And then divide everything by 2. I get y equals 1/2 x plus 1/2. That's a graph that crosses at a pretty gross 1/2. That's not as pleasant as we're used to. It goes up 1 and over 2, so you're going to notice that each time I go up 1 and over 2, I'm halfway in the block, because my y-intercept was a half value. Then take a second using a straight edge and get that line on there. It should be pretty quickly clear to you that these lines don't intersect. These are parallel. In fact, you can check that algebraically because the slope of the red line is 1/2 and the slope of the green line is 1/2. Because these are parallel, this is a no solution system. I use the no solution symbol for that. It does say tell whether it has one solution, infinitely many, or no solutions. So just to be clear, I'll write no solutions. These lines are parallel. This is considered to be an inconsistent system. It will never touch. Pause the video and do the you try it. So we need to talk about whether you can tell what kind of system you're looking at based on the equation. So without graphing, determine whether it's dependent, independent, or inconsistent. The first thing you definitely need to do is to put both equations into slope-intercept form, y equals mx plus b. Because if they're both in y equals mx plus b, you can kind of look at them and determine what's going on. If they're identical, so y equals mx plus b for both equations are completely the same, they're dependent. And the reason that is because they're essentially the same line. If you look at them and they have the same slope but different y-intercepts, they're parallel, which makes them inconsistent. They will never touch. No solution. And then the last option, of course, is if they have different slopes, then they're independent and will intersect somewhere. You don't necessarily have to know where, but you have to know that they will intersect at some point if their slopes are different. So the directions change just a little bit. It says without graphing, is each system independent, dependent, or inconsistent? So we're going to get them both into y equals mx plus b first. I'll do this top equation in green. Let's start by adding 3x to both sides. Adding 3x gives me y equals 3x plus 4. I'm going to box that so I can find it easier when I'm done the other equation. I'll do that other equation in red. X minus 1/3 y equals 1. If I want to solve this for y, I'm going to start by subtracting x from both sides. Leaves me with a negative 1/3 y equals negative x plus 1. And to get rid of that negative 1/3, I'm going to technically divide everything by negative 1/3, which is the same as multiplying everything by a negative 3. Times negative 3 cancel. Times negative 3 times negative 3. I get y equals positive 3x minus 3. So take a look at the red equation and the green equation. They're not identical. In fact, the y-intercepts are different, so they're not dependent, but they are parallel. When you look, the slope of the red line is 3 and the slope of the green line is 3. Parallel systems never touch. They are inconsistent. Parallel systems are inconsistent. All right, we're going to repeat that same process for letter D. I'll do this top equation in red. 2x plus 3y equals 1, and I'm solving it for y. I'm going to start by subtracting 2x from both sides. I get 3y equals negative 2x plus 1. And divide everything by 3. Gives me y equals negative 2/3 x plus 1/3. Box that so I can find it easily. I'm going to do the second equation in green. Solve it for y. 4x plus y equals negative 3. To get rid of the 4x, I'm going to start by subtracting 4x from both sides. I get y equals negative 4x minus 3. So I want to compare them. First of all, the red equation and the green equation are not identical, so they are not dependent. And they're also not parallel. When you look at the slopes, this one's a negative 4 and this one's a negative 2/3. So they're not parallel or inconsistent either. That makes this system of equations independent. They will intersect. I don't know where, and to be honest with you, I don't care because the directions don't ask for that. I just know that they will at some point intersect. Pause to do the you try it.